Hello everyone, I am Nishant from Sri Venkateshwara College of Engineering. Today I took the subject in DVTMS and the topic is principle of inclusion and exclusion. Introduction to qualifier in a computer science. Qualifier are essential tool in computer science and mathematics, enabling us to express properties and relationship about a seed and an element within those sets. They provide a concise and powerful way to express a complex ideas and particularly when working with a large data set or system. In hence, qualifier allows us to successively express how many or what proportion of object in a given set possess and particularly property. Universally qualified statement. A universally qualified statement asserts that a property holds true for every element in a set. We use the symbol for all to denote a universal qualification. For instance, the statement for all x belongs to R, x square is greater than 0 express that the square of all of any real number is always greater than or equal to 0. This is a fundamental concept in mathematics and has implementation across various areas of computer science, such as algorithm analysis and theorem proving. Example 1. All integers are either even or odd. In symbolic for a form, this is represented as for all x belongs to z, x is even. For all v is odd. This statement asserts that every integer x belonging to the set of integers z satisfies either the property of being even or a property of being odd. Example 2. Every natural number has a successor. In symbolic form, this is represented as for all x belongs to n, so that y belongs to n, y is equals to x plus 1. This statement asserts that for every natural number x, there exists another natural number y, that is its successor x plus 1. Exactly qualified statement. An exactly qualified statement asserts that there exists at least one element in set that possesses a particular property. We use the symbol there exists to denote existential qualification. For instance, the statement there exists x belongs to or x square is equals to 4 express that there exists at least one real number whose square is equal to 4. This statement is true because both 2 and minus 2 satisfies this condition. Extensional qualification is crucial in areas such as data analysis, where we often search for specific elements within large data set that meet certain criteria. Example 1. There exists a prime number greater than 100 in a symbolical form. This is represented as there exists x belongs to n. X is prime union of x intersection x is greater than 100. This statement asserts that there exists a natural number that satisfies both property of being prime and property of being greater than 100. This is indeed true, as 101 is a prime number. Example 2. There exists a natural number that is both even and odd in a symbolical form. This is represented as there exists x belongs to n, x is even for all x is odd. This statement is false, as a natural number cannot be both even and odd. Combining qualifier, quantifier, nested quantifiers. Even we can combine quantifier to create more complex statement. For example, the statement for all x belongs to R, there exists y belongs to R, y is greater than x asserts that if for every real number there exists a real number y that is greater than x. This demonstrates a fundamental principle of real number. They are unbounded. Nested quantifier are crucial in defining concepts in mathematics and computer science, such as limited continuity and compatibility. Step 1. A universal qualification. We begin with a universally quantified statement that applies to all elements in a set. For example, for all x belongs to R, meaning for all real number x. Step 2. Extensional quantification. Then we introduce an extension quantified statement within the scope of universal quantifier. For instance, x, y, for all y belongs to R, meaning there exists a real number y. Step 3. Relating the variable. We, we then relate the universally quantified variable x to extensionally quantified variable y through a condition such as y is greater than x, meaning y is greater than x. Quantifier and logical connectivity. Logical connectivity such as conjunction and minus and disjunction v minus or negation minus negation symbol minus not and implementation arrow minus if then are commonly used with a quantifier to create a more intricate statement. The order of quantifier and the use of logical connectivity are crucial in understanding the meaning and truth value of statement. For instance, for all x belongs to R of x square is greater than 0, x is not equal to 0 states that for every real number x its square is greater than or equal to 0 and x is not equal to 0. This illustrates how logical connectivity can be combined with quantifier to express a complex mathematical relationship. Connectivity symbols meanings. Conjunction symbol ulta v meaning and disjunction v symbol like v meaning or negation symbol like a small n shape meaning not implication arrow mark, meaning if then. Application of quantifier in algorithm analysis. Quantifier are a fundamental in algorithm analysis. They allows us to express the time and the space complexity of algorithm in a precise and consciousness manner. For instance, for all n belongs to n, there exists k belongs to n. T of n is lesser than or equal to k of kn, states that for any input size n there exists a constant k such that the runtime t of n of the algorithm is bounded by a linear function n. This statement indicates that the algorithm has a linear time complexity. Quantifier allows us to quantifier allows us to analyze the behavior of algorithm across all possible input size, providing a crucial insights into their efficiency and scalability. Example: consider an algorithm that search for an element in a certain array. Its time complexity is zero of log n, indicating that the algorithm running time grows logically with the input size. This can be expressed using qualifier as a for all n belongs to n, there exists k belongs to n, t of n is lesser than or equal to k of log n. Quantifier quantifier in a programming language and logics. Programming language and logics often incorporate quantifier to express condition and a relationship within a program. For instance, in a programming language like a Python, the statement for a x in list can be interpreted as for all x belongs to list, illustrating through all element in the list. In a logical programming, quantifier are used to define rules and relations between object. For example, the prologue statement for all x for all y, parent x, comma y, ancestor x comma y, express the rule that if x is parent of y, then x is a ancestor of y. Quantifier provide a foundation for expressing and reasoning about a complex relationship within program and a logical system. There are three: loop illustration, logical reasoning, function definition. Loop illustration means quantifier implementally defines the range of a value that loops variable illustrate over in a programming language. Logical reasoning. Quantifier are used in a logical programming to express a relationship and a rule between object, enabling sophisticated reasoning and problem solving. Function definition. Quantifier can be used in the definition of function to specify the domain and range of function as well as the relationship between input and output value. Thank you.